series, so I'm going to discuss very briefly, because that's a technical but important point, renormalization of gauge theories. Then I'm going to start to discuss some physical issues, some physical properties of gauge theory, in particular the most important property of non-abelian gauge theories, which is asymptotic freedom, which makes them very different from QED, and some other point depending on the time. Okay. So first, let's discuss renormalization. So now we have constructed, as people did in the beginning of the 70s, all the tools to study the theory, of course, in perturbation theory. So we have our gauge field, A mu, which belongs to the Lie algebra or to the adjoint representation of SU2. Well, I'm going to consider SU2 or a general Lie group. Okay. And we have the original Yang-Mills action, classical Yang-Mills action, which is minus 1 over 2g times, well, let's call it g squared, integral of d4x trace of f mu nu. F mu nu, where f mu nu is a stress tensor, the curvature tensor associated to the A mu. So f mu nu is d mu A nu minus d nu A mu, and minus or plus, I never remember why. Let me just check. I should know this by heart, but I'm sorry. This is minus I A mu A nu, and this is the important new term in non-abelian gauge theories. And in order to perform consistent quantization, well, we need to fix the gauge by a gauge condition that I'm denoting in a very sketchy way, f of A. It's a function, some local function of A and its derivative equals 0 at any point. So that's okay. And then we need that when we fix the gauge, we need to add to this in order to define a path integral. We need to add to the path integral over the gauge field a path integral, a Grassmann path integral over ghost and anti-ghost. So these are the standard vector field. These are the ghosts. So they are spin 0 but fermions. Okay. And then, well, we can enforce the constraint by adding a Lagrange multiplier that I was calling lambda, but I think in my note it's called B. So this is a Lagrange multiplier. And the final action, so IS, is S Yang-Mills of A plus S ghosts of C bar and A. And then the term that fixes the gauge, which I can denote just B times F of A. So this is that when you integrate over B, you get integrate over B of exponential I B times F of A. So this is just a definition of the Fourier transform of delta F of A equals 0. So this represents the delta f of A, and this construct the determinant of df of a gauge transformation of A. So that this is one. Okay. And so this is a very schematic representation of Gauss. And we have seen that the action of the Gauss is just C bar D of f of E C. So it involves a coupling between the Gauss. Okay. So the rules is that we have, with these rules, we have a propagator for the gauge field, which is a standard. It's Maxwell. It's exactly like in the Maxwell theory. So it behaves like 1 over k squared, but of course with some indices where k is a momentum. Okay. For the Gauss field, we have a propagator which behaves also like 1 over k squared. And we have a coupling. So we have a coupling between the Gauss field, which is proportional to g times some momenta k. So if you have some momenta k here, that comes in some momenta. So it's some g times some k with a lot of Lorentz and group factors that I'm not writing here. I'm just writing the degree of what's going on here. We have a 4 vertex, which is just over the g squared, a 4 gluon vertex. So this is an A term. And finally, we have the coupling between the gauge field and the Gauss fields. That involves if this is the momentum k of the outgoing Gauss is proportional to g times k. Again, with a lot of Lorentz and group indices that reflects the fact that the total action is invariant. Okay. And if you want to add matter fields, so if you want to add fermions, real fermions, Dirac fields, of course, you are going to have the standard propagator for the fermions. So between so this is between psi and psi bar, which behave like 1 over p, 1 over k, because it's 1 over k slash. Okay, let's write it k slash. So it's behave like 1 over k, and we have the standard coupling between the Dirac field and the gauge field, which is over the G times with, again, some gamma matrices and some group indices. But basically, that's the same kind of coupling than in QED, but decorated by the group structure. Okay. So the whole Lorentz group and Dirac indices are commuted. Okay, here, very sketchy notation. Okay, so now, and we have seen that since we have gauge fixed, for instance, the propagator of the gauge field has the same nice properties than in QED, namely only the transverse physical degrees of freedom of A mu propagates freely like plane waves. That's the 2 degrees of polarization of an electromagnetic waves. And they do not mix with the other degrees of the unphysical degrees degrees of freedom of the field. So now, when non-abelian gauge theory is considered, of course, the problem of quantizing the theory is much more difficult because you have the interaction. So basically, if we go to one loop, and we want to compute the correlation functions of in order to compute the S matrix element of a gauge bosons, you must compute the correlation function and then apply the LSZ rule. So you have to compute the two-point function. And you are going to see that, for instance, for the two-point function of a gauge field, okay, this is going to be the original propagator, but then you are going to have one-loop diagrams, and one-loop diagrams, there are three kinds of, well, four, but first you have this kind of diagram that involves two creation and alienation of a pair of virtual gauge field. Okay. Then, and of course, this is of order G squared. So again, well, so one loop means order H bar or order G squared. Okay. Then you have this kind of diagram, which is the same than 5 to the 4, except that it's decorated with a lot of indices. And then you have, of course, you may have an internal loops of ghosts. And remember, the ghosts are fermions, so they go from C to C bar, the propagator. Okay, so you have a ghost. Okay, and well, if you had fermions, you would have a loop with an internal loop of fermions, exactly like a QED. But I'm not going to write it here. Okay. Okay. So this diagram has symmetry factor. I omit symmetry factor. Symmetry factors, because this is going a very sketchy discussion. But so all those three diagrams are of order G squared, are given by some complicated amplitudes. The important point is that since the, is there a red, no red chalk? Well, okay. The important point is since the ghosts are fermions, the standard rules of integrals over Grassmann variable supply, and you end up, when you apply Wick theorem, etc., to the fact that there is a minus sign, because the ghosts are fermions. Okay. And, well, the same thing for the three-point function. We discuss the three-point function. Well, I'm going to discuss mostly three. So you have the three-point function. So the three-point function, this is the tree-level diagram. This is the term of order G, and then you have a term of order one-loop diagram, and one-loop diagram can be created in many ways. So you may have this diagram. You may have this kind of diagram. You may have I think that's all. Well, let's compute the irreducible. Of course, I compute the irreducible diagram because the other one can be obtained in this way. So I get this one. And so I think I'm not forgetting any diagram for the 3-point function. And then I get, of course, a diagram where you have ghosts. Okay. So here you have an interaction vertex. You have 3 points. You have all the possible permutation of the legs, etc. So here you have an internal loops of ghosts. So there is a one loop, one ghost loop. Okay. And this comes again with a minus sign. So this term is over the G, this term is over the G cube, G cube, G cube, because this is over the G, over the G, over the G, this is over the G, this is over the G squared, okay, etc. So all these terms are the terms, the one loop diagram, okay? And, well, again, you can write the 4-point function. And you should notice that, in fact, you also have, well, let me write them here. You have the possibility to have a 1-point function because you have this possibility and this possibility. Okay. And let me write the 4-point function. This is going to be the vertex. And then you are going to have to be, well, you have a lot of them. Well, not that many. You have an internal loops of gauge field with 4 vertices. You have something like that, where here you have 2 3 vertex and 1 4 vertex. You have this, where you have an internal loops of bosons, but you have 2 4 vertices. Okay. And then again, you have ghost loops with 4 vertices, you see. Okay. And again, with a minus sign. Okay. So you see the diagrammatics starts to be flourishing. And of course, when you start to have all the possible contraction of indices, it becomes a bit complicated. This is not infinitely complicated, but this gives you an idea of how things are going to be complicated when you go to higher loops, where this has been a okay, so this is for the gauge field, but of course we have the ghosts. So we must compute. So this is a 1-point function. This is a 4-point function. Okay. And we have to consider what is a 2-point function and the for the ghosts. Because they interact with the gauge field. And, well, that's going to be like in QED. So this first you have the propagator, and then you are going to have to be this kind of diagram, which is the same than in QED. Okay? Yes. Okay. And then you must have the interaction vertex for gauss plus gauge field. So the 3-point function where you have a gauss that interacts. Well, so this is a gauss tensor. So this should be a dashed line. Okay? Because we have a vertex here, interaction vertex for the ghosts. Yes, this one. Okay? And it gets a radiative correction. So this is going to be the original vertex. And then we have, well, the same diagram than in QED. Oh, no. We don't have the same diagram than in QED. We have this diagram. Well, they look like the diagram in QED. And we have this diagram. See? Okay. So this diagram contains the ghost gauge vertex. This diagram contains two gauge ghost gauge vertex and one gauge vertex, and this one contains 3. So this one is of order G, and this is of order G squared. Okay. So this is a one-loop contribution. This is a one-loop contribution, and those diagrams are one-loop contribution. Okay. So these are the diagrams we have. Okay. And now, well, let me just keep this. Okay. We must analyze the ultraviolet divergences. And there are lots of possible ultraviolet divergences. Because the propagators behave like 1 over k squared. This propagator behaves like 1 over k squared. But remember, for instance, that this vertex contains a k term. So for instance, if you consider this, these diagrams behave like 1 over k squared, but they might be a momentum k coming from the vertex and a momentum k coming from the vertex here. So this could behave like d4, I'm in 4 dimensions. This could behave like d4k divided by k squared. So there is a potential, let's write this in green. There is a potential lambda squared divergence. Okay? And then there may be a subleading divergence in p squared with some times log lambda. Okay. The same here. Okay. This could diverge like lambda squared. So and this could diverge like lambda squared plus p squared log lambda. Okay? I omit again all the Lorentz indices, the group indices, etc., which are very important. Okay. Here, this is the same thing. This could diverge like, well, you have a 1 over k squared, 1 over k squared, 1 over k squared, but you may have a k, k, k. So this could diverge like lambda, okay, plus some momentum, some of the momentum here, times log lambda. Okay? The same here, and the same here. Okay. So that's quite bad. Okay. Now, the point is that gauge invariance implies that the lambda squared cancels. Okay? They cancel between the three diagrams. And most importantly, they cancel between the contribution of the loop of gauge field and the loop of gauge. So in fact, because we have a contribution that comes from the gauge loop minus the contribution of the gauge loop. Okay? So we have a factor which gives 0. So the fact that the ghosts were fermions is a crucial step. Okay, so first step, the two-point function. So okay. But the second important point is that because of gauge invariance, the you know, remember, the two-point function was behaving like, well, in fact, the two-point function was behaving like 1 over p squared times some tensor p mu nu of p, where p mu nu was essentially delta mu nu minus p nu divided by p squared, plus, in our case, something depending on the gauge, on the depending on the gauge fixing parameter. Okay. Okay. And the important point, the important property of this p mu nu is that when you consider a transverse mode, so if you consider a polarization epsilon mu for the gauge field, which is transverse to the momentum. So epsilon mu, so that's epsilon mu p mu equals 0. Then this doesn't depend on the gauge fixing parameter. So it's gauge invariant. Okay. And if you consider a longitudinal mode, then only these terms. So epsilon mu, if epsilon mu is proportional to p mu, this term disappears. this term is non-zero, but it's p squared over p squared p mu. So you see longitudinal modes propagates independently. Okay. And this is realized because of the gauge invariance. That's because the coefficient of all the Lorentz and Grump indices manage in a way to build something which is gauge invariant. Okay? Okay, so this is for the two-point function. This is for two-point function. And the same thing happens for the three-point function. The lambda, dangerous lambda coefficient disappear. Well, in fact, they disappear because of parity, so it's a bit simpler. But they do disappear. And what remains is a divergence in log lambda. Okay. So now you also have to check that. So let's go back to the two-point function. Oh, that I haven't written that. We also want to have that gauge invariant is satisfied at one loop. And this requires, in particular, that. No, okay, I already told that. So let's go to the three-point function. Okay. So you get the coefficient of log lambda, but you want to check that gauge invariance implies that if you have a longitudinal modes, if you extract from this the S matrix element for 2-to-1 body interaction, if you have two physical transverse polarization mode, you cannot come out with an unphysical longitudinal mode. So this turns out to be related to what are called the Ward identities that I have no time to explain, but basically they mean that if you insert a longitudinal polarization here and elsewhere transverse polarization, this gives zero. So basically means that, remember, this object is this object contains an index mu. It contains some group index, etc., but it contains mu, nu, and rho. So in fact, it's a 3 tensor. It's a function of p, so it's a function of the momentum p here, okay, and or the other momentum. And what you want is that if you have p mu times this object with mu, if you contract it with p mu, with here physical indices, this gives zero. Okay. And you can check that this is satisfied for the vertex. I wrote the 3 vertex explicitly, so you can check that. But it's not obvious that this is true at one loop. And this is going to be true. This is going to satisfy, again, because there is a cancellation between the gauge loop and the ghost loop. Okay, so again, ghosts are crucial to satisfy gauge invariant. If you have forgotten the ghosts, or if you had made a mistake in your calculation, you would have got something wrong. Okay. Now so now thanks both to parity and gauge invariance, this is equal to be 0. Okay, and that's quite fortunate, because otherwise you had a mu term. Okay. So these diagrams could contain a lambda divergence, but again there is a cancellation. And finally, these diagrams, well, if you start to count, these diagrams can contain some only log of lambda. Log of lambda, because this is, where does the 1 over lambda, yeah, because this is 1 over k squared times a k. You may have a momentum here. You may have a 1 over k, 1 over k, 1 over k. So all these diagrams contains log lambda, log lambda, log lambda terms. Okay. And finally, this diagram may contain, so this behaves like P. So these diagrams may contain, this is a 1 over k squared, this is a 1 over k squared, but there is a k, so it may contain a lambda plus P times log lambda, and this term disappears. It's not present. Well, that's the same, in fact, there's the same argument that in QED. This diagram is easy, okay? And here, again, this diagram contains, may contain 1 over k squared, 1 over k squared, 1 over k squared, but there may be a k here and a k here. So this means a 1 over k6 times k squared. So it contains a log lambda. Okay. So these diagrams contains a log lambda. And this diagram contains a log lambda. Okay. And you can check that the word identities, the fact that P mu times a vertex here with physical degrees of freedom applies also to the 4-point function. So if you have P mu times this that depends on mu, this is equal to 0 also. And again, this will come out from a cancellation between the gauge field loops and the ghost loop, okay? So I'm not doing any calculation, I just tells you what's happening. Okay, good. So this was Blackboard 2, this was Blackboard 3, and this was Blackboard 4. Okay. Okay, so now, so you can check thanks to gauge invariance and thanks to the ghost, in fact, now you can analyze the logs. So you have only logs, only log lambda divergences. Okay, and this was already, in fact, let me check that this was already something non-trivial, because Yang-Mills theory were proposed by Young and Mills in the 50s, and they were not taken very seriously for many reasons in the 60s. One reason being that since theoreticians didn't know how to treat in a proper way gauge fixing, it took time to develop this ghost formalism, and this Faddeev-Popov determinant thing. People doing naive calculation were finding those lambda squared divergence, which were meaning that so if you started from massless vector particles, massless because there was some gauge invariance, radiative correction would give them a mass and the mass of the order of the cutoff. So it's like generating a cosmological constant. So, and this was, for this reason, many physicists were not considering non-Abelian gauge theories seriously because they were thinking that there was this problem that were strongly not renormalizable. Okay. But, okay. So we have only logs of lambda divergence, but now we have to check that. So we have that, in fact, we have to check that those divergences are proportional to terms of the same form in the Lagrangian. And you see, in the original action that is written here, if you expand f mu nu and the Gauss term, there is you cannot choose independently the coefficient of the 3 vertex and of the 4 vertices and the vertex. The structure of the interaction term for this, and this, the couplings, the form of the couplings, namely the algebraic structure plus coefficient. So how they can be written in terms of Lorentz and gauge indices. So they must be dictated by the structure of the algebra, of the Lie algebra of the group and the Poincaré invariance. The couplings are strongly correlated, strongly fixed, and only G, coupling constant, remains as a parameter. Which means that if you have a coupling G here, you must have a coupling G squared here and G squared and G here, but you cannot choose this to be 2G squared. Okay. So, if the theory, for the theory to be renormalizable, okay, namely, in order for the logs to can be recasted into a coefficient in the action, the various log lambda terms must satisfy this relation. Must satisfy this relation. The same relation. If finally at one loop you have a log lambda here and you have a 2 log lambda squared here, well, you have a 2 log, you don't have a, you have a 2 log lambda and not log, the corresponding log lambda, everything fails. Okay. And, well, this is, in order to do that, you have to check that the word identities are, still satisfied once you introduce counter terms. Okay. And well, in fact, there is a more involved version of the word identity, which is called the Taylor identities, but I won't discuss that. Okay. So you see, these are the problems that the people met when studying the renormalization of gauge theories in the end of the 60s and the beginning of the 70s. Okay. And the solution of this problem at one loop, in fact, was solved, I think, around 71, 72, by Gerhard Toft, and then Gerhard Veltman, okay, who showed by an explicit calculation at one loop using the trick of dimensional regularization, that indeed, if you did things properly, you find that it was renormalizable. Okay. The theory is the Yang-Mills theory is renormalizable. Okay. So this comes, perhaps 15 years or even more, 20 years after the creation of Yang-Mills theory. Okay. And this immediately had a very important consequence for the physics, of high-energy physics, that I'm going to discuss a bit later. Okay. So a general proof was provided a bit later, I think by various authors, but I think the first one, which is not often very well acknowledged, was by Lee and Xing-Justin. This is not T.D. Lee, the famous Lee of T.D. Lee of parity violation. This is not the Lee of Li Yang and or the not the Lee of Li Yang. But another Lee who died, I think, a bit later. He died quite young. Okay. And a very elegant proof of renormalizability of phi-4 at all, of Yang-Mills at all order was provided by elegant and important formalism was provided by Becky, Wei, Stora, plus some Russian guy that independently, that name starts by T, but I'm unable to spell it correctly. I have not, okay. This is called the BRST formalism. In fact, they show that there is a symmetry of the gauge fixed action. So in general, if you gauge field the gauge theory, use the gauge field, you have lost everything or almost everything of gauge theory, of the gauge invariance, because you get rid of the huge gauge symmetry that was physically redundant. But they show that the gauge, once you have a gauge symmetries, so you have a theory with ghosts. In addition to the gauge field, you have a theory with ghosts. This theory has a hidden symmetry, which is not obvious on what I wrote here, which is a symmetry that mixes the generator of the symmetry mix ghost and gauge field. So it's a supersymmetry. That mixes the A, the C bar, and the Lagrange multiplier. And I may say a word about that. Because it's an important tool also in many areas, in particular in string theory. Okay. So this is and all of this was done in the 60s. I think this was done in 67 or 6 or 67. And this was done in 60. No, this was done in the 70s. So this was 75 or 76, and this was 77, I think. Okay. 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 Good. So the final result, and I'm going now to discuss what is a beta function. So this was 4, this was 5, this is blackboard 6. So now I'm going to discuss the second point. Very big, yes?
So that the generator of that symmetry mixes ghosts with the gauge fields.
Yes.
They're like fermions and bosons.
Yeah, but that's because the generator are fermions themselves. So when you, the generator, well, if I have I may say a word, but the generator of this symmetry are fermionic generators. It means that when you write the variation of a if you want to transform a boson field into a fermion field, you can transform it by a fermion generator times a bosonic field. Then it becomes a fermion. And if you make a variation on a fermionic field by stating that it is the fermionic field times another fermions, it becomes a product of two fermions that are boson.
What I meant is since ghosts are fermions and
yes.
gauge fields are bosonic,
yes.
they're raising and lowering operators and everything.
Yes.
Have certain commutational and
yes.
anti-commutational relations.
Yes. You're right.
And since it's a symmetry, after applying the generator,
yes.
it should still have those same commutation and anti-commutation.
It depends how you define your symmetry. Well, I don't want to go into the detail because then I would need to define what it is. I might have the time, but think, you have heard about supersymmetric theory in high energy physics. Well, you know that well, since 30 years, people are looking for supersymmetry in nature, and there are very good theoretical reasons for that. Maybe the nature is not supersymmetric. But the supersymmetry theory, that's the minimally supersymmetric standard model extension, these are supersymmetry that are supersymmetric extension of the Poincaré group, and they mixed fermion and boson. Because, for instance, you know, quarks or leptons have partners which are bosons which are supersymmetric. You have the S quark, which is a boson. You have the S lepton, which is supersymmetric. So this is also a supersymmetry, a symmetry that mixes, that transforms, that associates bosonic fields to fermionic fields. So it's exactly the same problem.
So,
same question.
So you're saying that the commutational relations are not concerned?
No, of course. This is consistent. Now, if you think of it in terms of Hilbert space, you may very well have an Hilbert space as part of the Hilbert space. You know, it's a product of the Hilbert space for bosonic and the Hilbert space for fermions. But those are two Hilbert spaces. So the total Hilbert space, the Fock space of a theory of the fermions is H bosons times H fermions. Okay. And so you have two Hilbert space. Okay. And you may very well have a symmetry between the states in this Fock space for bosons, Fock bosons, and Fock fermions. And if you have a symmetry that associates to states, these states, even if you know, you have operators acting on this that satisfies anti-commutating relation, and here you have operators here that allows you to construct the.
So
this is a symmetry between this is a symmetry between operators.
So are you
between
going
states.
To mix local operators there with non-local ones there, and the other way around?
Well, maybe like that. I'm not completely sure, but this is a symmetry between states. You can associate. If you want to, you can
and
group.
Also between operators.
You can group a state with fermions and a state with boson in a supermultiplet that is treated. Yep. Okay,
yep.
Let me stop there because I'm not at that stage, and I'm not an expert on supersymmetry. I never worked on supersymmetric theory in high energy physics, so I dealt a bit with this kind of supersymmetry, which is simpler. Because it's not a supersymmetric that applies on that mixes with the Poincaré group. Something much simpler. Okay. Okay. So now the result is that the total result is that. So let me compute the beta function. So the outcome of the study of renormalization of phi-4 theory, at least at one loop, is that basically you have as it was for phi-4, you have two renormalizations. You have to renormalize the coupling constant, the coupling. Okay, so the coupling has to be treated as a renormalized coupling that depends on the scale. Since you have logs, you have the same phenomenon that we discussed at length in, for phi4, and you have the renormalization of the field. So basically, A, C, and C bar have to be renormalized in some sense by writing that A renormalized, you have a renormalized phi that is a Z times A, etc. Okay. So that's exactly like for massless phi4. Okay. Where massless phi4 requires a renormalization of the coupling constant. We study it at length. And it requires a renormalization of the field phi, but only when you go to second order to two loop. So the difference between phi4 is that we have a renormalization of the coupling G at one loop, but a renormalization of the field phi only at two loop. Here, both renormalizations are required at one loop. Okay. And that's exactly like in QED. So technically, it's much more difficult, but the outcome is that the renormalization of non-abelian gauge field, it renormalizes exactly like QED. The only difference between QED is that QED is a free theory if it's not coupled to fermions. So it doesn't require renormalization. But if you couple it to fermions, both the charge and the electromagnetic potential have to be redefined. And while for Yang-Mills theory, this renormalization is needed and occurs, even if you have no coupling to fermions, because the fields are self-interacting. Okay. And now, so I'm not going to present any detail, but the calculations are a bit complicated, but you can find them in any good textbook on, like for instance, the Peskin and Schroeder textbook, or well, standard other books that treat an abelian gauge series. So it's a few pages. But the final result is that since they are logs, they are going to have a dependence in the scale. So you are going to have a running coupling constant. Running coupling constant. Okay, and the renormalization group equation for this running coupling constant is given by a beta function. Okay. And so the coefficient of the beta function for this, the coupling G, and let us rather write it like, in fact, the coupling constant is G squared, but let me write it for G. Okay. The beta function for G is G squared. There is a 1/4 pi squared. That's the usual coefficient that comes from the integrating over one loop diagram. But then you have a lot of coefficients that come from the group symmetry. And the final result is that this is given by, okay, I'm going to give the final result as you find it in textbook. For a general group, this is minus 11 divided by 3. Don't ask me where this comes from. It's come from the diagrammatic. And the coefficient that depends on the group, C2 of G. And if you have fermions, Dirac fermions, you have a 4/3 NF and the coefficient C of R. So I'm going to explain what this is before. Forget about that. So this is, so we have a group G. Let's assume that it's simple. It means that it has some, and NF fermions in a representation R of the gauge group. So if this was Dirac fermion, this would be the fundamental representation. Okay. And this is a result of a calculation. And this calculation was first performed for, I think, SU2 or SU3 by Toft. Was the first correct calculation. But he was a bit, he was young, it was a bit shy about that. So, in fact, calculation was not fully appreciated. It took some time, and then it was done for SU2 by Gross and Politzer. Gross and Wilczek, I'm sorry. Wilczek. And independently by Politzer, a bit later. So this was 72, I think, and this was 74. And they realized that it was important for strong interaction. Okay. And the important point is that, okay, this coefficient C2 is just something that is called the, it's a coefficient, it's a quadratic representation. It's called the quadratic Casimir operator associated to G. Okay. And the important point is that for a group SUN, the C2 of G is N. Okay. And for R equals the fundamental representation of G, the C of R is 1/2. Okay, this has just some, comes out from some group representation theory. Okay, so this is important. So in particular for SU2, this is going to be 2. SU3 is going to be 3. Okay. And the important point is this, I'm sorry, the important point is this minus sign. Which is very important and which came out as a surprise. Nobody was expecting that, or almost nobody, I think. And that's very important because that's different from phi4. For phi4, remember, the beta function of G was 3 over 4 pi squared G squared for phi4. Which means that the running complete constant goes up at high energy. For non-abelian gauge theories, the fact that there is a minus sign means that the running complete constants, or the effective complete constant, if you want, as a function of the energy, goes down when the energy E goes up. So the higher the energy, the weaker the interaction. Energy. The weaker the interaction. Or if you prefer, the smaller the charge. Okay? The effective charge. And this result was very important because at that time, in the beginning of the 70s, there were a famous experiment at SLAC where high-energy physicists were probing the interior, the inside of hadrons, protons and neutrons, by sending very energetic electrons. Well, by nowadays standard, it would be very low energy electrons, but they were very energetic at that time. They were probing the inside of the particle, and they were experiencing the fact that inside the nucleon there should be some subconstituents that are called partons. And it seems that the higher the energy, the weaker the interaction with the partons was, which was something very surprising. And Gell-Mann and other physicists had developed a quark model with some symmetry, but it was still a bit phenomenological for saying these partons should correspond to something we call quarks, and they are classified as according to some symmetry. There was a famous SU3 group for quarks that was classifying the different quantum numbers that should have those quarks, but there were no real field theory behind that. And once Gross, Wilczek, and Polisser did this calculation for SU3, they immediately say, the good theory to describe the interaction between quarks inside the nucleon is an SU3 gauge series, because it has all the right symmetries and the right quantum numbers, and it is asymptotically free. Therefore, this explains why the quarks behave as a weakly interacting particle inside the nucleon. Okay, so that's a well-known history, but that was historically the breakthrough that changed the face of high-energy physics at the beginning of the 70s. Okay, so I think we should have that. So this property of the fact related to the fact that the beta function has a negative sign is called asymptotic freedom. So this is asymptotic freedom. And it's in the ultraviolet, namely high energy. And you see that this property stays true as long as you have not too many fermions. Okay. And of course, this formula contains the result for QED, because QED is a U1 theory. And so this, why did I say that this is N? Yeah, it's a U1, so SU1, well, but SU1 is just trivial. So basically this term is absent for QED. This was for SUN, not for UN. So a U1 factor doesn't count. So you get only this factor, and this is the result for QED with a plus sign. Okay. Okay. So asymptotic freedom is the essential property of non-abelian gauge theories, and it can be viewed as an anti-screening effect. The fact that quantum electrodynamics is not asymptotically free can be viewed as the fact that when you have a charge, for instance, an electron here, and you want to study how it interacts with another electron, that's the way you measure the charge. Okay? You measure the force exists. And in the quantum theory, in QED, well, you have creation and alienation by quantum fluctuation of plus and minus so you have a cloud of virtual E plus E minus particles. That pops out, well, that's a semi-classical picture, but that pops out of the diagram, and which are represented by the diagram, okay. And, well, it's a very well-known classical effect that occurs in classical physics, which is called Debye screening, which is when you have an ionized liquid, with anions and cations around the charge. Well, if you have a minus charge here, the plus charge prefers to be attracted. The minus are below, and this screen the charge. Okay. So this screening here due to quantum fluctuation, by quantum fluctuations, decreases the effective charge is smaller than the microscopic charge. In fact, screening in a liquid means that it's complete screen. The charge at some points gets completely invisible. Okay. Here, it's not completely screened, but there is some screening. And the point is that this is an anti-screening effect due to the pair of virtual gauge bosons. And that's explained by the fact that anti-screening effects due to the nonlinear interaction in Young-Mills. Because remember, you have this 3-vertex interaction, or this 4-vertex interaction, which means that when you apply, for instance, if you apply an electric field, it's going to create. If you apply an electric field, imagine there were no electron, pure Maxwell. If you apply a big electric field, nothing happens. But if you applied a non-abelian electric field, then plus and minus particles will appear because the gauge fields interact with itself. Okay. And there are some arguments which say that this is going to create another electric field that creates a magnetic field, and basically that counters acts. Okay, so there's an anti-screening effect, and it's quite phenomenological, but you can find a nice description of this in the book by Peskin and Schroer. Some model explaining in a bit unwavering argument why there is anti-screening. Okay. Okay. So now, an important consequence of asymptotic freedom is, of course, that interactions becomes strong at large distance. Okay. And this is going to explain, in a sense which is not completely mathematically, the phenomenon of confinement. The phenomenon of confinement is that although the small, at the microscopic level, the theory involves gauge bosons. If you want charged photons, okay. But in the theory of strong interaction in QCD, they are called gluons. Gluons because they glue things together. Okay. And in a pure Young-Mills, you have only gauge bosons, so you have charged photons. Nobody has ever observed a free gauge bosons. And moreover, if you have fermions, which are of course charged, which correspond to the quarks for QCD, they are not observed either. Okay. And the reason for that is that since the theory is strongly coupled at large distance, the coupling becomes so strong that, for instance, the electric, if you want, the electric potential between two quarks. So imagine that you have two very heavy quarks charged with a charge plus and a charge minus. Of course, this is a very sketchy notation because remember the charge are charge of a SU3 group. So you have for a quark 3 different kind of charge. But let us say that you have a quarks with a quantum number A and an anti-quarks of the same. So they form a singlet of a SU3 group. Okay, and this one has a charge plus the unit of charge, which is 1/3 for SU3, and this has charge minus 1/3. Okay. Well, no, I'm mixing the electromagnetic charge and the. Okay, so these are the charge plus, and these are the charge minus. Okay, so they should attract each other. Okay. And the point is that as a function of the distance, well, if this was Coulomb potential, if this was, QED, Coulomb, the potential will be just 1/r, potential V of R. Is expected to behave like 1/r at short distance. Okay. But there are a lot of arguments and calculations that indicates that V/R behaves like R at large distance. So basically, the quarks, at large distance, they are linked together by a spring. And the higher the larger dimension, the higher the energy. And the energy grows like R². No, the energy like, yeah. No, that's not a spring. A spring, it should be, no, it's a spring, like a spring. Like a spring. Okay. So, you never get a threshold where a pair of quark of an anti-quark gets, ionized. Yes?
For a spring, isn't the force linear in R and the potential quadratic?
Yes. All right. No, I'm sorry. Yes, you're right. So it's not like a spring. It's like a string. Sorry. Yeah, I'm sorry. I used the incorrect word. Okay. Yeah, the potential goes like R. So it's like what's called a string model. Okay. And anyway, this is sufficient to get confinement. So this is a phenomenon of confinement. Okay. So there are a lot of phenomenological models static plane confinement. There are a lot of, so you have models. For instance, you have a model which states that this is the analog, the electric analog of the magnetic Meissner effect. In superconductors. So in the same way that in superconductors, the magnetic field is screened, the vacuum of QCD is an electric superconductor. But I won't discuss that. This scenario is supported by Monte Carlo and high temperature, but strong coupling calculation. In lattice gauge series. I have no time to explain how you can discretize the gauge series on a lattice, but this is a well-known subject. In fact, this method, this has been devised by Wilson, Ken Wilson, around 74. The same Ken Wilson, the Ken Wilson of renormalization group. Okay, and well, nowadays there is a lot of studies in trying to prove confinement in supersymmetric gauge series. Of course, ADS, CFT plays a role, etc. I'm not very familiar with all of this, but it's still not proven mathematically that the phenomenon of confinement occurs. But basically, well, the reason why we expect confinement is that becomes interaction strong at large distance, and interaction becomes strong at large distance because the beta function has a negative sign. And this effect should continue unless. So, I have 5 minutes left, so maybe, well, I could start to discuss something else, but it will last. I could speak about this BRST symmetry, but I'm afraid it could take more than, well, it could take 5 minutes, but it should be very, very quick. So perhaps I just could, well, just let you ask questions about what you would like to know and you are, or you find wasn't clear in the course, and we have some time to discuss. Unless there was something else, I just, something important that I can explain in 5 minutes that I have not explained. But no, you have no question. Absolutely.
How long are you still around?
Yes, I'm around this afternoon.
Great. And then you're going back?
Pardon?
You're going back up?
I'm going back over the weekend in Europe, yes. Yeah, I'd like to have stayed more. So this was a very, very sketchy introduction to gauge theories, but I think if I want to discuss more, I would like. Well, I can explain to you how you define the gauge theories in a very sketchy way, if you like. No? A lattice gauge theory. Okay? Because that's I can just explain what it is. And, so the idea is how do you, this is a real. So lattice gauge theory. Gauge theory. just the receipt. Okay. Because it's a nice receipt due to Wilson and also to a Connors matter and statistical mechanical German physicist called Wegener. 74. Okay. So remember, if you want to have you want to discretize a QFT involving scalar fields. See, so fields phi of x that are located on some point, and this may come out as a continuum limit of the Ising model, for instance. You take a lattice. And at each site, I, belonging to Z D, let's say, the lattice ZD, you associate a variable, which can be an Ising spin SI equal plus or minus 1, or a continuous field phi high, which is real, or phi of x. So that's the trick. And then you write an energy functional by taking derivatives. So you write that, for instance, that d phi squared is going to be phi I minus phi g squared for an edge Ig. So the coupling is associated to the hedge. Okay. Now for the gauge field, things are different because this is a vector field. So the field is A mu of x, but rather than thinking of A mu of x, view this as a one form. Which is a connection. So it describes in mathematical terms how you transport yourself, how you change the electromagnetic field when you transport itself. So the trick of Wilson is not to associate the variable to a site, but associate the gauge variable to an edge. An edge, E. So to each edge E here, you associate a variable G of E, which is an element of the gauge group. So it's a matrix. Okay? And strictly speaking, if you consider an edge, the edge is oriented. Okay? So it's an oriented edge. And if you reversion, so if you take the edge, you associate G minus 1 of E. Okay. And now, a gauge, so this is the gauge field variable. And now a gauge transformation. A gauge transformation means that I associate to each site I an element of the group, let's call it U of I. It also belongs to the group G. Okay? And going from a gauge configuration G of X to, well, GE of edge to GU of edge, this is a gauge transformation, a local gauge transformation. It just amounts to multiply by the G here, for instance, that's the choice. So you take U of I, G of edge times U minus 1 of G. You see, when the edge, for an edge, E equal IG. You see? So the gauge fields lives on the edge, and basically G of an edge is something like 1 plus I times A mu of x d x mu associated to the edge, basically. So if G is very, very slowly varying, A mu is just something like this. You see? So the gauge fields A mu lives on an edge. This explains why it carries an index mu, because it depends on the direction. And performing gauge transformation is simply multiplying and dividing by the extremities. Okay. And gauge invariance means that you need to have an energy functional for this configuration that do not depend on gauge transformation. And so basically, the gauge invariant observable are just that you take a closed path a closed path. Let me call it C. Okay, and you just take the products, the oriented products of the G of E along the path. So you take GE1 times GG2 times GC, etc. You see, and you take the trace at the end. Okay. Trace of this G times this G and this G, and you can check that this is invariant. And this is called a Wilson loop associated to a path. So for scalar fields, the observable are simply correlation function between, so associated to pairs of points, associated to points. Observable in a lattice gauge theory are associated to paths. Okay. So that's the trick. That's a beautiful way to discretize space-time and still having defined a full-fledged gauge theory invariant field theory. Right. Yes?
Yeah, so if I define a gauge quantum field theory,
yes,
but not the lattice version, just the continuous
yes.
version.
Yes.
There are correlation.
Yeah, but
are these things?
Yeah, but the gauge invariant correlation function are defined exactly in the same way. They are defined as the ordered product. Let's go to write P, the path ordered product of exponential of I integral over the contour of A mu of x dx mu. Okay? And when you take the trace of that.
So those are the only gauge invariant things you can calculate
well, you may know. Well, and in particular, of course, you have trace of F mu. This is a gauge invariant quantity. But you can check that this object, well, you can fix, you imagine that you fix mu and nu. Okay? This is still gauge invariant. It's not Lorentz invariant. So let's say mu 0, nu 0, mu 0, nu 0. Okay? Okay. This is a gauge invariant, but I don't sum over the indices.
But you can only evaluate both of them in the same points, right? No, wait.
No, that's at the same point. That's at the given point.
Yeah. Yeah, so that's a quantity which is gauge invariant.
This is gauge invariant.
It could be physical.
It's not Lorentz invariant, but it's gauge invariant. Okay?
Sum over mu and mu.
Well, this corresponds to defining, taking a Wilson loop, which is just a single plaquette, where this goes in the direction mu. This is E mu, and this is E nu, the unit vector.
So your point is that you can write any gauge and Lorentz invariant observable as a Wilson loop.
Well, a Wilson loop will not be Lorentz invariant, because if you make a Lorentz transformation, it goes to another loop.
Yeah, okay.
But you can basically build.
You can sum over.
Yeah,
over
you can basically build. I think, well, almost all gauge invariant observable in terms of Wilson loops of some sort. Okay. Yes.
So this program seems very similar to what is done in loop quantum gravity, where the group elements are the holonomies of the connection.
Yeah, I'm not very familiar with loop quantum gravity, but in fact, the idea of loop quantum gravity came out, I think, by I think it's Ashtekar who invented loop quantum gravity. It was inspired from kind of idea that can be divided for lattice gates. Yeah, because loop quantum gravity means, I think, as far as I remember, I attended several courses, in particular a course by Ashtekar a long time ago. I think the idea is to formulate, well, canonical gravity as some kind of gauge theory. It's not exactly a standard gauge series because you have additional constraint, etc. But it's some kind of, so it's a theory which involves gauge degrees of freedom associated to the connection, etc. and the local Vierbein, and then use method of ideas coming from lattice gauge theory to quantize it. Yeah. But so there is a relation, but I think historically the relation came from applying lattice gauge series to some version of canonical general relativity.
So then my question was that, is there a way to associate curvature to the Wilsonian loop? Maybe just as in loop quantum gravity.
Well, in curvature in the gauge field or in the space-time?
Space-time.
Well, here I took a regular lattice, but of course, this can be defined on a non-regular lattice. It's more complicated, but I think it can be done without any difficulty. And so you can define, for instance, take a curved space-time, and discretize it by considering an abstract four-dimensional lattice with curvature, and then define a gauge theory on it and see how it reacts to the various concepts. There is no conceptual difficulty in doing that.
Thank you.
Yeah.
Last question. When you were drawing the 2-point function,
Yes.
I noticed you didn't have a chartful diagram with the ghost.
Yes.
Why did you omit the diagram?
Pardon?
Why did you omit the diagram with the ghost?
Why did I do that?
Yes, with the.
Yes, that's because it's possible. You have this vertex of interaction. So realize that you have this vertex of interaction between the tadpoles, which is the one I draw it over. You have this vertex of interaction, which is an interaction between the tadpole and the ghost. You see, so you can very well, when using the Wick theorem, contract C and C bar, and you get a tadpole. But the only point that this diagram is quite trivial because you see, if this is a momentum k that's centered here, the momentum k is flowing here because the only momentum that can flow here is p equals 0. Okay? So you have delta of p, so it's a pure number. And the amplitude for that is d for k divided by k squared, and then you have a k mu here. So first you have here a gluon, a gauge field with index mu, a polarization mu, but 0 momentum, which is a bit problematic. But then the amplitude of this is d4k over k squared k mu. So this diverges like a log, like lambda, if you want. But because of parity, if you change k in minus k, you change the sign of this integral. So this is 0 by parity. So it's lambda times 0 by parity. Of course, this argument requires that you have regularized the theory in a way which respects parity. And then otherwise you may have a problem. But basically, there is a Danvos lambda, but it is 0 by parity. But even if you had regularized the theory so that it was not 0 by parity, I think you would have a cancellation between this and this by gauge invariance. Okay, well, I took too long as I was expecting, explaining something was too long. Okay, so thank you very much for your attention and your passions and your questions. And well, you are welcome to ask more questions while I'm still there. It was a pleasure to be once again participating to this very wonderful PSI program. And I wish you, well, both good luck. You need some luck and success, and for that you need to work, but I'm not worried about that in the future of your studies here and whether you choose to do research and go to some other fields. I wish you more success and happiness. Thank you.